This lecture is part of a series of lectures on modular forms and will be about classification of modular forms. So the modular forms we're going to classify, first of all, they're going to be level 1, which means they're modular forms for SL2 of Z rather than for some subgroup of SL2 of Z. And secondly, they're going to be holomorphic, which means holomorphic on the upper half plane and also at I infinity, as we explained last time. So last lecture we found some modular forms. We found modular forms 1, E4, E6, E8, E10 and so on, and these had weights. 1 had weight 0 and E4, E6 and so on had weights 4, 6 and so on. And we also noticed that E8 seemed to be the square of E4 and E10 seemed to be E4 times E6. In general, it turns out that all these Eisenstein series, and for that matter all modular forms, can be written as polynomials in E4 and E6. And we will show that the ring of modular forms is more or less the ring of polynomials in E4 and E6. You have to understand this as being a graded ring. And more precisely, what we mean is that ring of modular forms of weight k are just the weight k elements of this polynomial ring, where of course E4 and E6 have weights 4 and 6. So in order to show that all modular forms are polynomials in E4 and E6, we need a key lemma. This says the number of zeros of a modular form f of weight k in a fundamental domain of SL2 of Z is k over 12. And you've got to be a little bit careful here because you need to count the zeros in the right way. You notice that if k equals 4, we seem to be claiming there is 1/3 of a zero in the fundamental domain, and well, we'll explain what this means a little bit later. So in order to count the number of zeros in a fundamental domain, we recall there's a nice formula for the number of zeros of any holomorphic function in any reasonable region. You just take 1 over 2 pi I times the integral around the boundary of the region of its logarithmic derivative, which is the derivative of f divided by f, and with respect to tau. And there's a neat way of writing that. We can write this as 1 over 2 pi I times the integral over c of df divided by f. Which saves having to remember what tau is. And now we should remember what the fundamental domain looks like. So first of all, we have the unit circle of centre 0, and the fundamental domain must lie outside this circle. And then we have these lines of real part 1/2 and minus 1/2. So if we take the strip of width 1 between these two vertical lines, and the bit of that above the circle is the fundamental domain for SL2Z. There's a bit of a problem. We want to integrate round the outside of this fundamental domain, but the fundamental domain is infinite, so we need to cut it off at some point. So we're going to chop it off at the point where the imaginary part is equal to t. So here we have a line going from minus 1/2 plus it to 1/2 plus it. And we choose t sufficiently large that all the zeros have imaginary part less than t. So now what we want to do is to integrate round the boundary of this domain, and we can see that there are 4 bits of the integral to deal with. There are 2 vertical lines, and there's a horizontal line with imaginary part t, and then there's this circular bit at the bottom of the fundamental domain. And fortunately, it turns out we can work out all of these integrals as follows. First of all, let's work out the sum of the integral over the vertical lines. So these are the integrals over the vertical line. Well, the sum of these is equal to 0, and this is because f of tau is equal to f of tau plus 1, because it's a modular form. So f has the same values on these 2 vertical lines, but in one of them we're integrating upwards and the other we're integrating downwards, so the integrals just cancel out. So that's easy. Next, let's do the integral over the horizontal bit. So we're integrating over the horizontal bit, where we're integrating from a half plus it to a half minus it. And now we make the change of variable. Q is equal to e to the 2 pi I tau. And as tau goes from a half plus it to a half minus it, what Q does is it goes round a little circle round Q equals 0 once in a clockwise direction. So we want 1 over 2 pi I of the integral around this little circle of df over f. And this is just equal to the number of zeros of f at q equals 0 when f is considered as a function of q, or rather it's minus that because we're integrating clockwise rather than anti-clockwise. So this is equal to minus the number of zeros of f at q equals 0, which is minus the number of zeros of f at tau equals I infinity, because we define the number of zeros at tau equals I infinity to be like that. Now we have to deal with the integral over the curved bit at the bottom of the boundary. And here we've got to integrate from omega, a cube root of unity, to omega plus 1 along this circular arc. And in order to do this, we're going to use the fact that f of minus 1 over tau is equal to tau to the k times f of tau, another of the modular form relations. Now we split this integral into two bits. We've got an integral from omega to I and an integral from I to omega plus 1. And we notice that tau goes to minus 1 over tau, maps the curve from omega to I to the curve from omega plus 1 to I. So what happens is that when we work out the integral of df over f, you can see the integral over these two circular arcs almost cancel out. And what we're left with is 1 over 2 pi I times the integral over 1/12 of a circle of d tau to the k over tau to the k. You can see if we didn't have this tau to the k here, the integral over this bit would exactly cancel out with the integral over this bit. But since we've got the tau to the k in, when we integrate this, we're left with d tau to the k over tau to the k over one of these little bits here. And this is easy to work out because it's just, you can see it's just k over 12. If we went all the way around this circle, it would just be the number of zeros of tau to the k which would give us k, but since we're only integrating around a 1/12 of the circle, we only get a 1/12 of that. So we find the number of zeros of f in the upper half plane is k over 12 minus the order of the zero at infinity. So we find the number of zeros in the fundamental domain is equal to k over 12, where here we include the zeros, 0 at I infinity. So this is the result we wanted to prove. However, there's one slightly fishy problem that we haven't yet talked about. And that is the problem of what happens if we have a 0 on the boundary. So I was implicitly assuming there are no zeros on the boundary, but in fact you quite often get zeros on the boundary, so we need to know what to do about that. And if we've got a 0 on the boundary, we can't integrate through the 0, so we can go round it in a little circular arc, or more generally, the boundary might have a sort of kink in it where this makes an angle theta. And again, we have to integrate around, if we've got a 0 exactly on this angular point, we have to integrate around it in a small sector of a circle. And what happens is that here this counts as theta over 2 pi of a 0. And similarly, if we've got a 0 on a straight bit of the boundary, this just counts as a half of a 0. And this is actually very natural, because if we think of a 0 as being a sort of small disk, you can see that here half the disk lies in the fundamental domain, and here a fraction theta over 2 pi of the disk lies inside the fundamental domain. So we sort of really are, pretending the 0 is a little disk and counting what fraction of that disk is in the fundamental domain. The reason why this works is that if we integrate around a simple pole, so if we go all the way around a simple pole, the integral round a simple pole would be of fz dz would just be the residue of the pole. However, if we integrate around only an angle theta in a small region, so the limit of c, which makes an angle theta of fz dz, tends to theta over 2 pi times the residue, provided f is a simple pole. So if we insert that back into the formula for zeros, we find that zeros on the boundary have to count as fractional zeros in the way that I've stated here. So to summarize, our result is the number of zeros is equal to the weight over 12. So this is the zeros in the fundamental domain, except that first of all we have to count the 0 at I infinity, and secondly we have to count fractional zeros on the boundary. By the way, you might wonder where this number 1 over 12 comes from. Well, what it really is, 1 over 12 turns out to be the area of a fundamental domain divided by 4 pi. And the area of the fundamental domain, well, you might look at the fundamental domain and say that's silly, its area is obviously infinite, but you have to work out its area with a funny volume. What you do is you use the volume dx dy over y squared, which is in fact, if you think of the upper half plane as being hyperbolic space, this is the volume of hyperbolic space. And one nice thing about this is it's invariant under the group SL2 of R acting on the upper half plane. So it really is a very natural volume. The area of the fundamental domain of SL2 turns out to be pi over 3. And if you replace SL2 by some other group, then you find this formula still holds, that the number of zeros is the area of the fundamental domain divided by 4 pi, except you have to count zeros at all the cusps and you count fractional zeros. And the area turning up is actually very natural, because if you've got a group, if you sort of had a fundamental domain that was twice as big, you would obviously expect to get twice as many zeros, because if you've got twice as much area for the zeros to be in. So in general, the zeros would be the weight times the area of a fundamental domain divided by 4 pi. And now what we're going to do is to use this result to classify all modular forms. Well, these modular forms are, of course, we're going to be holomorphic, and they're going to be on SL2 of Z, and non-holomorphic ones and ones on groups other than SL2 of Z are also very interesting, but we're going to do these ones first because it's the easiest case. So let's look at the modular forms of various weights. What about weight 0? Well, for weight 0, well, let's write down the number of zeros. The number of zeros is also 0 because that's k over 12. And the modular form, well, 1 is obviously a modular form of weight 0, and there can't be any others, because if there was another one, you could subtract a multiple of 1 in order to give it a 0 at I infinity, and that's impossible because it doesn't have any zeros. So let's write down the dimension of the space of forms. The dimension is just going to be 1. What about weight 2? Well, here the number of zeros must be 2 over 12, which is a sixth. And you can't get 1/6 of a 0. So if we look at the fundamental domain, you might say, well, you can get a sixth of a zero because it's got these two little pointy bits at omega and omega plus 1 where you could get 1/6 of a zero. Well, yes, you can. The trouble is if you get 1/6 of a zero here, you also get 1/6 of a zero at the other point, omega plus 1. So altogether you must get at least a third of a zero. So there aren't any modular forms of weight 2 and the dimension is 0. What about weight 4? Well, here the number of zeros is 4/12, which is a third. And we know of one form, which is E4. And as we said, the only way to get 1/3 of a zero is to have 1/6 of a zero at omega and 1/6 of a zero at omega plus 1. So here it must have zeros at omega and omega plus 1. And can we have any other forms of weight 4? Well, no, because if we had another form of weight 4, it also have to have zeros at omega and omega plus 1. So we could divide it by E4. And we'd have to get a form of weight 0, which should have to be constant. So the only forms of weight 4 are multiples of E4, so the dimension is 1. Weight 6 is kind of a bit similar. Here we want half a zero, and how can we get half a zero? Well, you might think, well, anywhere on the boundary will give you half a zero. Well, that's true. The only trouble is if you take a point here, it will have half a zero, but you'll also get half a zero from the other point corresponding to it on the boundary. So every point on the boundary except for omega, omega plus 1 and I corresponds to another point. So the only way you can get half a zero is by having a zero at I. So E6 must have a zero at I. And similarly, any other modular form of weight 6 also has a zero at I, so you can divide it by E6 and get a form of weight 0. So the space of forms of weight 6 is one-dimensional. Forms of weight 8 is similar. Here we get 2/3 of a zero. So we must have zeros at omega, omega plus 1, omega, omega plus 1. It must have a double zero at omega and a double zero at omega plus 1 because that's the only way you can get 2/3 of a zero. So we have such a form which is E4 squared. And just as before, the space of such forms is one-dimensional. So E4 squared must actually be equal to E8 because the space of forms is one-dimensional. They must have zeros at these two spots, and they've got the same constant term, so they must be the same. And here, again, the space of modular forms is one-dimensional. For weight 10, this is kind of similar. We get 5/6 of a zero, and here the only way to get 5/6 of a zero is to have a zero at I and omega plus 1. So we get half a zero at I and 1/6 of a zero at omega and omega plus 1. And again, we could either take E4, E6 or E10 as our modular form, and these have to be the same because the space is one-dimensional by the same argument, and they've got the same constant term. Then we get to weight 12, and now things get a little more complicated. So there must be exactly one zero, and we can now think of three forms of weight 12. We can have E4 cubed, or E6 squared, or E12, and you can see these all have constant term 1, but they're all different because the coefficient of q is different. And the zero can be anywhere. Well, so what do we do? Well, let's write down the discriminant form delta, which is going to be E4 cubed minus E6 squared over 1728. And this is equal to 0 at I infinity because the constant terms cancel out. So where's 1728 come from? Well, that's the biggest number you can divide by to make the coefficients integers, as we'll see soon. And it's called the discriminant because it turns out to be related to the discriminant of an elliptic curve, but never mind that for the moment. So this form is weight 12 and has 1 0 at I infinity. So it's non-zero on H, the upper half plane, because it has 1 0 in a fundamental domain, and we've already found the 0 at I infinity. So that's very nice. And now we can show the space of modular forms of weight 12 is two-dimensional. So let's take any modular form of weight 12. You subtract a multiple of E4 cubed to make it 0 at I infinity. And since it's 0 to I infinity, we can then divide by the discriminant, because the discriminant is non-zero on H. So this is now a holomorphic modular form of weight 0, so it must be a constant, and there's only a one-dimensional space of these. So we see the space of modular forms of weight 12 is just two-dimensional. Everything can be written as something times E4 cubed plus something times delta. In particular, we've got three modular forms of this weight, E4 cubed, E6 squared and E12. So there must be a linear relation saying that E12 is equal to something times E4 cubed plus something times E6 squared. And I'll leave finding these constants as an exercise. You can figure them out just by noting that the coefficients of q to the 0 and q to the 1 on both sides must be the same, which gives you a couple of linear equations for these. So finally, we get to finding all modular forms, and for modular forms of weight k greater than 12 with k even, you can just repeat this. First of all, we can find a modular form of the form e4 to the power of something times e6 to the power of something of weight k, and this is equal to 1 at I infinity. And now if we've got any modular form, we subtract off a multiple of e4 to the something times e6 to the something to make it have 0 at I infinity. And we can then divide it by delta, and this gives us a modular form of weight k minus 12, which by induction on k is a polynomial in E4 and E6. So we see that any modular form can be written as a polynomial in E4 and E6 of the same weight as that form. So we say the ring of modular forms is the ring of polynomials in E4 and E6. Well, strictly speaking, elements of this ring aren't all modular forms. It's only the ones of a fixed degree that are modular forms. So we should remember this is really a graded ring, and it's the graded pieces that are the modular forms. We should check that E4 and E6 are algebraically independent. In other words, there's no polynomial relation between them. For this, it's sufficient to do look at the polynomials of fixed weight. And in order to show they're algebraically independent, I'll just leave it as an exercise and provide a hint that E4 is 0 at omega, but not 0 at I, and E6 is 0 at I, but not 0 at omega. And from this, you can easily show that all homogeneous relations between these are trivial. Okay, so that has classified all level 1 holomorphic modular forms. Next lecture, what I'm going to do is to classify the modular functions for SL2 of Z, which, as you remember, could sometimes be written as quotients of modular forms.